Okay, so for SL, the emphasis here that we're going to first start off with is the strength of acids and bases. What you need to remember is that strength has nothing to do with the concentration of the acid. It has to do with the ability to dissociate into ions. And so it doesn't matter if you have a 12 molar weak acid. It's going to be dangerous, but it's not strong at that point. I think a lot of people kind of use the word strong as dangerous, but it's not. They're not synonymous. And so there are two types of strength. There is strong, which dissociates 100%. Okay. So therefore, all of the concentration that you have will become ions. Okay? And so terms that you have under here are strong acids, bases, and just generally electrolytes. Okay? There are 3 acids the IB has you memorize: HCl, HNO3, and H2SO4. Bases, for our most part, group 1 hydroxides, and some of the bigger group 2 ones. So, know those because you need to understand that they dissociate 100%. Electrolytes are any solute that dissociates 100%, which allows it to conduct electricity. Because of the free moving ions. That's why a solution conducts electricity, because of free moving ions. So if they say a strong electrolyte solution, that means there's a high concentration of ions. If they say weak electrolyte solution, that means there's a low concentration, but there is enough to conduct electricity. If they say a non-electrolyte, that means there's no ions. And we'll kind of get to that in a second. Weak, dissociate very little. Oops, literally. Okay, little. Like about less than 1%. And so when you're talking about weak acids, that's everything else. Bless you. Okay? It's fine, it's on the recording. Okay.
This is like a class.
Oh, yeah. So, everything else. So, common weak acids that you should be familiar with: hydrofluoric acid, ethanoic acid, cyanic acid. Those are kind of the common weak acids that you see in reactions and equations. Again, bases is everything else. But the most common one you'll have is like NH3 or even, methylamine, which is CH3NH2. But you kind of have most of these nitrogen-like bases that can accept hydrogens. And they all fall under the category of electrolytes as well. Non-electrolytes are essentially solutions of covalent molecules. Okay, so things like sugar, like even like CO2 dissolved in water. Those don't conduct any electricity because they don't form any free-moving ions, which allows electricity to pass through. So keep that in mind. Questions about the types of strengths of solutions? Yes, Ida.
So if you make any covalent molecule like aqueous, it's going to be a non.
Correct. Any covalent molecule that's dissolved in water, unless it has, I guess, two polyatomics, because those are ionic technically, it will have no conductivity. Correct. So that could be a multiple choice question. Which of the following species does not conduct electricity when in an aqueous solution? So you look for something like sugar or CO2, just some kind of species there. Now, be careful about that because acids and bases aren't considered, I guess, covalent molecules here because they dissociate in water. So we're looking for like actual covalent molecules that don't ionize at all. Okay. No problem. So, reactions is a huge kind of segment of this kind of concept. And so we are going to do quite a few reactions here. And so something that's a strong acid or a base, you'll notice that it has a single arrow. Okay? A single arrow implies that the reaction is significantly forward, meaning that isn't very reversible. So strong acids and strong bases dissociate 100%. So therefore, if you start with 1 molar of this, you end up with 0, and you end up with 1 molar of each of these ions. They dissociate 100%. A little bit of ice chart, equilibrium. But also remember that if you have a strong acid that has 2 H pluses, then it doubles the concentration. Okay? And so if you have something like H2SO4 and it dissociates into 2H plus SO4 2 minus, and this is 1 molar, this is now 2 molar and 1 molar. Okay? Remember, the parts don't have to equal the whole when it comes to molarity. Okay? There are more independent species, and so the molarities don't have to add up. It's not like mass where you conserve it throughout the whole reaction. Moles are just counting particles, and so you can have more parts than whole pieces. A lot of students end up trying to divide by 2 because they're like, well, it has to be half of that. No, you actually have twice as many parts as you do whole. So that's really important to think about. With weak acids and bases, you have notice double arrow. Double arrow represents reversible reaction, so it goes forward and reverse. And so you have an equilibrium there. You have an expression of the rate of the forward and the reverse reaction. Okay. While we're here, we will label conjugate acid-base pairs as well. Okay. A base always forms a conjugate acid. An acid forms a conjugate base. But I don't want you to associate the word conjugate with the right side. That's not always true. Because when they say conjugate acid-base pair, they mean conjugate acid-base pair. Don't think of it as conjugate acid dash base pair. It's conjugate acid base pair. So if you think of this as NH3 is a base in this situation because it's forming an acid, and water is donating a hydrogen to become OH minus, then your conjugate acid base pairs are considered to be NH4 plus and NH3, or H2O and OH minus. So if they ask you that those are your two pairs. Because conjugate acid-base pairs can only differ by an H plus, that's it. So that would be probably a multiple choice question, just identifying. Actually, it was on your short answer too, so that is a possible question. Higher level, we will talk about ice charts with this, because you have to be able to calculate pH and pOH from knowing Ka or Kb and things like that. But for standard level, you're not dealing with equilibrium. No. No. You will focus mainly on calculating pH given concentrations already. Yeah. We will. Okay. Now, a couple of notes here as well. Okay. The stronger the acid or base, the weaker the conjugate. So if you have a very an acid that dissociates a lot, its conjugate base is much, much weaker. And I'm not saying strong and weak, I'm saying stronger, which is a relative term. Because most of these are all weak acids and weak bases, and so it's just a stronger or weaker acid or base. But so keep that in mind. And you look at strength based on your Ka or pKa values for acids, and then pKb values or Kb values for bases. Now, pKa means negative log of Ka. So, which means it's going to mean the opposite of what your Ka value is. And so, a stronger means a higher Ka, but a lower pKa. Because you take a negative log, it makes it the opposite relationship. So, for example, just to kind of keep things simple, if you have let's just keep it really simple. 1 times 10 to the negative 4, and then 1 times 10 to the negative 6, this is a stronger one. But when you take the pKa of that, that's 4 and 6, that's still the stronger one. So make sure that you know those values are related to that. Questions on that section there? Excuse me. I'm not sure how far the SL will go into that Ka and stuff like that, but just in case, it's not a bad thing to know the HL part. You're allowed to explain using HL stuff in the SL test. So if you know it and you want to use that to reinforce your explanation, that's fine. It's not like you can't use HL stuff to explain your SL. You're more than able to do that. Okay, reactions of acids that you need to be familiar with. Okay. First, an acid plus a metal. HA is your generic acid. It doesn't matter what A is. It could be Cl, it could be NO3 minus, it could be C2H3O2, but whatever acid that is. So if you have a huge acid formula and you don't want to write it out, you can write HA for your ice chart as a generic, and X being the metal here. You will produce a salt and hydrogen gas. What type of reaction is this? Single replacement or displacement. I know. So, as a tie into the other, this is a single replacement reaction or single displacement. But that also means it's a redox reaction. Okay, we're not going to get into this a lot, but your oxidation states are changing in a single replacement reaction always. So keep that in mind for kind of cross-curricular things.
In double replacements, does the oxidation level like not change?
Generally, no. Usually you're just swapping partners for that, so the oxidation numbers don't change. But single replacement, combustion, synthesis, those are all redox reactions. Okay. Next one. Acid with a metal oxide is going to form a salt and water. I don't know why I wrote X2O in this case, but I just wanted to make sure that you knew that X was a +1 charge. So I wrote that way. It could be XO and it'd be a +2 charge. That's fine, but just trying to keep things as simple as possible.
I'm gonna double fist the coffee.
It's okay, she doesn't know we're recording. Okay. So, another one, acid plus metal hydroxide. Again, you kind of see a pattern here. Salt and water. You can do a metal carbonate or a metal hydrogen carbonate, and you'll get the same products. A salt and water and CO2. Exactly. Always write it as H2O and CO2 as products. Never write it as H2CO3, because that's not the way it exists. It releases CO2 gas, because CO2 gas isn't very soluble in water, so it actually breaks up. The most common reactions, household reactions that you're probably familiar with like this, is like baking soda and vinegar. That's the basic reaction here. Baking soda and vinegar makes CO2 gas as they're reacting, because baking soda is sodium hydrogen carbonate, NaHCO3. And so it produces CO2 gas here. Now, just another note, these that produce gases, you can use that to measure the rate of reaction. Okay? So if they ask you, state a method of measuring the rate of reaction, with these reactions, you can just measure the volume of gas being produced over time. Yeah, sure. Okay. Measure rate of reaction by volume of gas produced over time. And you need to emphasize the over time, because if you're just saying volume of gas, that's wrong, because you're going to produce the same amount of gas no matter what. Your question is, how much do you produce over time? And this is also one of the ways that we can differentiate between a strong acid and a weak acid. Okay? And so that's kind of our next kind of transition here. Sorry, I'll move it back up a little bit. Okay. So, differentiating between a strong acid and weak acid. Equal molarity. I think that's kind of important, because you could make a weak acid lower pH by increasing the molarity enough that it dissociates enough to be more acidic. But here we have equal molarity. So this is kind of one of those conceptual questions. You're talking about how you would test it and what kind of results you would expect. Okay? And so if you have two beakers here of 0.1 molar acid and 0.1 molar acid, and what they usually say is other than pH. because they know that's the cop-out answer. Because if you measure the pH of the same molarity, your strong acid will be a lower pH because it dissociates more. So they'll say other than pH. Okay. Other than pH, identify which beaker contains, oops, I kind of merged words there, contains strong acid. Okay. And there's several ways. Yes, Steph?
When they say other than pH, would that also be like a concentration measuring?
Yes. Yeah, so that rules out titration, that rules out pH probe, that rules out any method to measure concentration of H plus sign. So don't try to be like sneaky and say titration. They don't want that. There, I would say two major ways that you could do it. Okay. One is conductivity. Okay, the strong acid will have high conductivity, whereas the weak will have low conductivity. And it's important that you state what the results are going to be. Anytime the IB asks you to compare two things and like how you would test to separate them, you need to say what you would expect to see. So you would say, I would test conductivity of two beakers, and the strong acid would have high conductivity and the weak acid would have low conductivity. You have to state that. You can't just say, I would test conductivity. You need to tell the IB what you would expect to see. So that's one way to do it. The other way is reaction rate with a hydrogen carbonate, a carbonate, or a metal. It doesn't really matter which one because they all produce a gas. So then you would say you'd measure the volume of gas per time. And so for a strong acid, it would have a faster reaction rate. And for a weak, it would have a slower reaction rate. Okay. Yes. The key thing here is that, remember, reaction rate is dependent on several factors, and one of them is concentration. Namely, in this case, of ions, because the metal the carbonates react with the H plus ions. A strong acid dissociates 100%, so all the available H plus ions are present to react. Whereas a weak acid, what it does is it reacts the little bit of H plus it produces, then makes more, then makes more, and then makes more until you run out. So therefore, it would be a slower reaction because there's less available collisions. Okay. So those are your two techniques. Yeah, Katharina. Yeah, they don't. Yeah, so for conductivity, they don't actually like ask you to specify how you would test conductivity. But yes, you could do a light bulb. A strong acid would light the light bulb brightly, and then a weak acid would light it dimly. But it would still light it. So don't say no conductivity because that's wrong. There is some conductivity, it's just very weak. Questions about that? Okay. Now, let's see. The last reaction that we really focus on is, I can't really write a generic one here, that doesn't really work out, but is an acid plus a base yields water and a salt. And the salt is a combination of ions from the acid and the base that aren't the H and the OH. Okay. So you should be able to identify what acid and what base the salt came from. Okay, so for example, if I say something like KCl, what acid and what base did KCl come from? KOH and HCl, yeah. Just something like that. Just be able to identify where it came from. And it's pretty safe to add OH and H to the second part. This one's a little bit trickier, but what are your acid and base here? HNO3 and H3. Yeah. For a higher level, you'll have to be able to identify whether it's an acidic salt, basic salt, or neutral salt. But for SL, it's just a know how to make salts. And all of these reactions are exothermic neutralization reactions. So again, with the multiple choice, if they ask you which of the following reactions is exothermic, a neutralization reaction of an acid plus a base is always going to be exothermic for our purposes. Yes? Okay, that's a good question. So Katharina asked, how would you differentiate between a strong acid and a strong base? You're most likely probably just going to be able to put a metal in there to see if it reacts. Because a strong base shouldn't react with the metal. That's probably the way I would do it. Other than pH. I mean, obviously pH, I guess, is the easiest way to do it, right? But if I were to differentiate between a strong acid and a strong base, I would just add a metal or a carbonate and see if it reacts. Oh, so Katharina asked, like, let's say you had a beaker of a strong acid and a beaker of strong base. They look the same, right? How would you test to differentiate them? Well, I would put a metal in both, and the metal only reacts with the acid, and it doesn't react with the base. I haven't seen that question as much with that. I've seen this question with a strong and weak, because I guess it's just a little more obvious with that one. Yes, Steph?
Curiosity, but when you have a strong acid reacting with a strong base and a weak acid reacting with a weak base, do they emit different levels of heat?
Oh, okay, that's a good question. If you're talking about temperature change, yes, I would say so, because a strong acid and a strong base will react more quickly, and so the temperature change will be higher. For a weak acid and weak base, it's going to react a little more slowly, so while you're probably going to, while it's going to take the same amount to neutralize, it won't increase the temperature as much.
So would that be another method to differentiate between a strong acid and weak acid?
That's a little tricky. I haven't seen that actually offered in the mark scheme. And so the thing is though, I think if you extrapolate the final temperature back for both of them, you should get the same temperature. Because technically it should give off the same amount of heat. So that I wouldn't go with temperature in that case. Okay. All right. pH scale. Okay. Okay. Now, this is the general scale at 25 degrees Celsius. Okay, and so this is for SL. Now, remember, neutral is defined as the H plus is equal to the OH minus. It happens to be 7 at 25 degrees Celsius, but it doesn't have to be at 25 degrees Celsius to be considered neutral. So the definition of neutral is when H plus is equal to OH minus. It has nothing to do with the pH. So don't use that as your explanation either. Acidic is when your H plus concentration is greater than your OH minus concentration. And basic is the opposite. Okay. And so for SL, equations that I would know, to help, I would say, even though these aren't given to your, some of them aren't given to your data packet, I would still say know these because I think it'll make your life a lot easier. Okay? The pH and the pOH ones are pretty straightforward. It's always negative log of whatever you're talking about. So H plus and OH minus. So you don't need to memorize both, just memorize pH and you'll know all the rest of them. The reverse of that is H plus concentration is equal to 10 to the negative pH. And likewise with OH minus concentration. H plus times OH minus is equal to 1 times 10 to the negative 14, which is kW for higher level, but for standard level it should just be 1 times 10 to the negative 14, which then makes pH plus POH equal to 14. Now, since this pH scale is on log base 10, what that means is that for each unit of pH, how much does the concentration change? 10, a factor of 10. So 6 to 7 is 10 times, 5 to 6 is 10 times. So it's okay. 5 to 7 is 100 times. So it's a factor of that. So keep that in mind, because for SL, what they'll do is they'll say, I'll write that down. So what they'll say is a 10 centimeter cube solution has a pH of 4 and is diluted with 990 centimeters cubed of water. Determine the new pH. So this is an SL question, multiple choice, or maybe even short answer. So what you have to understand is you're going from 10 to 1,000. So you've changed your concentration by a factor of what? 100. So therefore you've changed your pH units by 2. Right, because 100 is 10 to the 2. So this is 2 pH units. Now, if you're adding water, which direction on the pH scale should it be moving? Toward the basic, toward 7. So therefore, your answer here is a pH of 6. I guess let's just say toward 7, because if I have a base and I'm diluting it, it's going to go toward 7. So it's going to be less OH minus, so it's going to become more pH. Water makes it go towards 7. I think that's a kind of general rule of thumb. So understanding that each pH unit is worth 10 times concentration, really important. That's a conceptual thing for especially SL. That's usually what they take advantage of in the multiple choice, because you don't have a calculator, so that's how they test to see if you actually understand what pH is. Questions about that? Tenfold change. Know these equations. If I were just to pick 3 to know, I would know those 3, because you can figure out the other 3 from that. So minimize what you have to memorize. Yes, Elena.
Wait, sorry, can you explain the last thing again?
Oh, the 4 to 6.
Yeah.
Okay. So a solution has a pH of 4, and you're diluting it by a factor of 100 times. So the pH is going to change by 2 units, because 10 to the n equals 100. So it's 2.
How do we know exactly?
Oh, because the volumes. So it's going from 10 to a total of 1,000. So that's a factor of 100 times the volume change. So that's a factor of 100th of the concentration. So their pH is going to change by 2. And you always, if you're diluting, you always change towards 7. Questions about that? Okay. Don't hesitate. Even if I'm recording, you're more than welcome to ask questions. Okay? And unlike normal class, I can't really berate you. I have to pretend to be nice because this is documented. So I will compliment you on your good questions, and I will grit my teeth and smile when they're bad questions. Okay. I'm glad you can't see my face on this video, though, because that would probably be a problem. Okay, the major one, 8.5, acid deposition. This is the new environmental aspect application of the IB, okay? So it's going to probably be on there, okay? One of the environmental applications will be on there, whether it's acid deposition, whether it's ozone layer, or it's incomplete combustion, or if it's, I guess it's not really greenhouse effect because that's more energy, but some of these applications, they're going to find a way to incorporate on here. And acid deposition is a fair one, okay? So remember, normal rainwater has a pH of 5.6. It is always naturally slightly acidic. Okay, so acid deposition, we'll kind of get into that. So why is because there's CO2 dissolved, which then makes carbonic acid. That's why it's slightly acidic. Yeah. So acid deposition is anything under 5.6. And so this is where you need to know those reactions, where they ask you about the nitrogen oxide reactions and the sulfur dioxide reactions. And so we'll go over these now. So NO2 plus water yields HNO3 and HNO2. I think they like to ask this one because it's less likely that someone could figure it out on their own. Like the sulfur dioxide, sulfur trioxide, you just combine it together and you get the answer. But this one, you actually have to have studied it to know what the answer is, because you won't know off the top of your head that nitrogen will both oxidize and reduce at the same time. And so, which it does because N is plus 4 here, and then it is plus 5 and plus 3 here. For non-IB information, this is called a disproportionation reaction, when something oxidizes and reduces in the reaction. So tying into redox again. Okay. The sulfur dioxide plus water forms H2SO3, and then the sulfur trioxide with water forms sulfuric acid. So knowing those reactions for acid deposition are going to be important. And also knowing the sources of this. Okay? And so that's what we're going to get into here with, they call them NOxes and SOxes, like nitrogen oxides and sulfur oxides. NOxes come from, one, internal combustion. Oops. Because N2 gas combusts with fuel as well. Actually, no, let me rephrase that. N2 gas combusts alongside fuel. I don't want you to think that the fuel's reacting with the N2. The N2, because it's so hot in the chamber that some of the N2 reacts and forms nitrogen oxides. Okay. And also, naturally, so internal combustion would be the artificial method for making nitrogen oxides. Naturally, essentially the decomposition of vegetation or plant life. Is it vegetation? Yes. Yeah. Vegetation, plant life kind of naturally release that kind of through the nitrogen cycle. So artificial, and then a natural contribution. Oops. SOXs, or sulfur oxides, come from one, burning of coal, because coal contains sulfur in it. But it also comes from volcanoes. Volcanic eruptions throw up a lot of sulfur into the atmosphere as well. So that's your natural method of producing SOXs.
Isn't it also like decomposition or not as much?
Probably not as much, at least not from what I've seen. Like, I would say that these are safe answers if they ask you for that. So if they say, state one natural cause of the production of NO2, you would say decomposing plant vegetation, or volcanoes for sulfur oxides. Okay. Now, okay, ways that we can remove sulfur from coal, because that's our main source of producing sulfur oxides. Now, I'm really annoyed by this, because I think I've said this before, but for pre-combustion, all they say is just remove sulfur. So, like, that's all they say. Like, I used to spend like half a class period talking about, it's called froth flotation. So what you do is you mix the coal into water, and then the water separates, you like aerate it, and then sulfur floats and the coal sinks, or actually sulfur sinks and coal floats, and you can scrape off the coal, and then sulfur kind of stays in the bottom. But they don't ask that. They just say you remove the sulfur from the coal physically. Okay. The post-combustion is the one that's more used, which is the scrubbers. Okay. So chemical scrubbers in the smokestacks. Okay. And that is some form of calcium, wait, hold on a second. Calcium oxide. Yeah, calcium oxide. Because that reacts with the SO2 to form calcium sulfite. So what they do is they spray the exhaust gas once you burn the coal off with calcium oxide solution, and then that bonds to the CO2, it precipitates into solution, falls in a solution, then you can collect that and try to recycle it. I think you can take that sulfite and then convert it into sulfuric acid. Okay. Okay. Now, again, so those are removal of sulfur. Last thing for SL reactions with metals and carbonates. So again, you have something like H2SO3 with something like magnesium. You'll get H2 gas, then magnesium sulfite. So reactive metals like iron, reactive metals like copper, magnesium, and stuff like that. And also, again, you have the carbonates, where you have like calcium carbonate, which is limestone, which is used in statues and buildings and things like that. And so you form calcium sulfite, which is soluble in water, and then H2O. So that's how things deteriorate. Okay. Sorry, I said last thing and then I lied. Okay. One more thing I thought about. Okay. Effect of acid deposition. Okay. So a couple of different effects that you want to, if they ask you, state and explain two effects of acid deposition. One, it's the, I guess, don't know if you want to say weathering, but we'll say chemical erosion of buildings and statues made out of like limestone or metal ones as well. I mean, but and also, yeah, like essentially it accelerates kind of the rust. But so lowers pH of bodies of water. Yeah, ocean acidification, which kills marine life. Because once you start lowering the pH of a solution of a lake, then you have an issue with not being able to get enough oxygen in the water. And so then marine life starts to die off. I think once you get to like about 4.5, which is a 1 unit of pH, a lot of fish starting to die. And then I think after 4.0, it's uninhabitable. Like I think it's just dead. And so they're trying to find ways to kind of help buffer that. I think those are the two main ones for effective acid deposition. Okay. Limestone, yeah. CaCO3 is limestone. I'll write that down there. Yeah. Okay. Questions about this? Okay.